So, let us get further into HPC. So, there are various kinds of machines and various kinds of programming style. Okay. And so, you are using a machine, then you need to know what kind of machine that is, and also what programming environment are you going to use. Okay. So, I think this part is critical for programming. So, classification I am going to discuss today. So, shared memory architecture or shared memory machines. In fact, we saw in a node, within a node, right, we had processors here, cache. So, these were part of a chip and memory was separate outside. This was for ROM processor, right, a ROM processor, memory was outside, and of course, processor talks to memory via switch, well, some interface. I discussed about crossbar switch, no. So, we need to have, so any processor should be able to talk to any memory. So, this is crossbar interface, and the GPU can also be connected. Okay. So, sometimes HPC, if GPU is the most prominent hardware, then we will need to access GPU. So, this memory is shared by all processors and GPU as well. Okay. Then this called shared memory. Okay. What is the advantage of this? Advantage is basically, so the example which I was thinking of, you have this Microsoft document, okay, and 4 of you want to edit it simultaneously. So, should we keep this document in different memory or same memory? Same memory, no. So, that is the advantage of shared memory. So, the 4 people are accessing that memory, and well, only thing is, if you are trying to change one word and somebody else is trying to change the same word, then there will be a problem, but there are ways to take care of that aspect. Otherwise, when many people can work on the same database or same document or same memory, okay, like banking system, they do not want to have separate memory for separate users, right. So, that is the advantage of shared memory, and this is, yeah, you need to think broadly how to program that kind of system. Okay. So, this is also called unified memory. By the way, I want to make a remark that M1 chip, Apple's M1 chip has memory inside the chip, and that we said is unified memory. Okay. I used the word before. So, Apple in fact memory is inside the thing and which is shared by all of them, CPU, GPU, also neural engine which is for AI. So, they all use the same memory block. Fast memory access and lesser management, as long as of course, you need to make sure that 2 people do not hit the same memory location. Okay. And in the standard programming for CPU, this is the strategy OpenMP. If you have shared memory system where we have lots of CPUs and lots of memory. So, typically this is, well, not typically, it is a single node system. I am going to describe what node is in 10 minutes. So, in a single memory system there is only one server, and within a server there are many processors. It could be there could be 256 processors, okay, even 5, well 2. So, 4 ROM will be 256 processors, right, I mean which is easily available nowadays, well not easily, but there are machines which have 4 ROM inside, or I could have 512, I can put 4 AMD which is with 128 core processors. Okay. So, and for that you need to use OpenMP, and so we will see that we do not need to send data across 2 processors, okay, which is convenient. OpenMP programming is easier than other programming architecture called MPI. Okay. So, message passing interface. So, that is part of the next computer design, distributed memory systems. So, here we have two nodes. So, we will see very soon what a node is. So, there are two, you can think of two big machines or two servers. Now, I am going to run one program in the full node 0 and node 1. Okay. So, some part of the work will be done in this machine and some part of the work will be done in this machine, okay. But they need to talk, okay. Because sometime, well, imagine we have big array and I want to do a sum of the elements of the array. Okay. So, I can say, well, half the data is summed in processor 0 and half data is summed in processor 1. But so, we will have local sum of node 0 and sum of node 1, and finally, we need to get the total by summing up that local sums. And so, that is where we need some communication. So, it is possible that node 1 will send the data to node 0 and node 0 takes the responsibility of okay, I am going to add your data and give the final result to the user. Okay. So, this can be like head of the department type, So, he takes all the data and sends it across. Okay. So, this is called distributed memory, and you see the memory is distributed. This memory is separate than this memory. This guy the node 0 cannot access memory of node 1 directly. So, this processor cannot simply go and talk like that. It has to go via it has to go via interconnector. I mean, you can see that in fact, they are disconnected hardware. Okay. So, this is called non-uniform memory access, NUMA. It is different memory at different places, and so nodes are considered processors and memory, and I discussed that. Okay. And this programming style is called MPI, message. Do I have the full form here? Okay. Message passing interface. Okay. So, there are two ways to program a CPU based machine. GPU based machines are programmed very differently, okay. But we suppose we have a okay. So, it is possible, okay, there are something called hybrid programming. In hybrid programming, I may do OpenMP here. So, look, the problem is how do node processor 0 and processor 1 communicate? Okay, that is the problem, no? So, do they share the memory here or like processor 0 and processor 1? This memory also will be okay. So, you understand, no, there is a memory system here, and one way to do is to say that I am going to divide this memory into 4 parts, okay, and each processor has its own distinct memory. Okay. The program will do it, the MPI library will do this division, and processor 0 will not talk to processor the memory of processor, well, processor 0 and processor 1 have separate memory. So, even within a node we can run MPI, and then we have separate memory for each processor, and if they want to talk, then they have to send and receive across the memory in the same node. I hope this part is clear. So, essentially I will start for this two systems 8 MPI processes. Each node has separate MPI process. Okay. That is one way, and of course, within this machine they do not go to the switch, but there are ways to talk, exchange data in the memory itself. So, nowadays in MPI, programmer does not need to worry about it. Programmer just says send data from processor 0 to processor 1. Okay. There are ways to do it, we will learn that later. So, it is easy, it is simple one function, but had it been OpenMP, then memory will not be divided. This processor can access the memory anywhere. These are two differences, but there is one called hybrid method. What is hybrid method? Within the node, within this node, I do OpenMP. Okay, I get a sum, I need to get a sum. So, I can say, well, let the memory be shared, I will do a local sum within the node. This node also I do OpenMP, but then we have MPI for sending data from here to there. So, this is called hybrid, is mixing of OpenMP and MPI. It has advantages, but the speed up we are not getting much, or in fact no significant improvement in present hardware. Okay. There are reasons for it, but and writing hybrid code is slightly complicated because we have to have OpenMP and MPI. So, okay, so either, well, but we will see OpenMP is much very easy. In fact, we need to write few lines and the program, sequential program becomes a parallel program. But we already in thinking of parallel programming. Okay, I am dividing the work among processors, that means it is parallel programming. In real life, parallel programming is, suppose I run a big course and have 1000 copies to grade. I will go crazy if I grade 1000 copies alone. So, we take help of colleagues and TAs. Right? So, divide work. So, let us say 100 copies each, 10 TAs. Okay. So, same thing is done here. This is distribution, this is parallel programming. Okay. So, there are basically two ways to program in CPUs, OpenMP or MPI. Okay. So, let us look at our machine. Okay. So, the best machine in IIT Kanpur is Param Sanganak. We will arrange a tour. Okay. So, you can go and see this machine. So, this is called a rack, this object. Okay. It is a tower. In fact, tower is as tall as this, I mean is taller than a human being. Okay. It is probably going to hit the roof. And within this rack, we have nodes. So, you can look at, this is a node, this is a node and this is a node. These are called nodes. So, node is basically a box which contains motherboard, network switch, and motherboard has CPU or GPU or and RAM. Okay, CPU, GPU, RAM, and there will be a ports. Ports is data for basically link for the data port. So, data will flow in and out from these ports. So, every node is basically a block. So, you are right now we are desktop, no, the desktop is big, and if you fill the desktop in computer center, it is going to be basically whole CC will be filled up. So, these are very compact blocks where this high intensity processors and GPUs are installed. Okay. And there are enough cooling, desktop can stay in room temperature, but not these machines. So, temperature may be around 15 degrees of this server room. Okay. So, there are many nodes which are packed up here. Okay. So, our Param Sanganak I think has 6 racks, 6 of these racks. Okay. And it has probably 200 nodes. So, you can imagine each of them has 50 odd nodes or 40 odd nodes here. Okay. Now, these nodes have to talk to other nodes, right, data passing we saw. So, wires come out of each node from behind, this all closed. Okay. This part is at least closed. So, this open version, so they opened it up for us. So, these blue wires are fiber cables. Okay. These wires you can see, they are fiber cables and they are all coming out from each node, and there is a switch inside. Now, I do not know whether you can see it carefully. So, these wires are getting inserted in blocks. So, we will see a switch bit later. Okay. I will show you a blown up version of a switch, and this switch will so each these wires will go and get in the switch. So, switch is a box which has ports. Okay. So, there could be 48 ports, and these wires will get plugged in. So, imagine 48 ports means 48 guys are 48 nodes are getting connected to this port, to the switch, and then these 48 guys can talk among themselves. The wiring, I mean there are connections from here, well there are various sorts of connections within a switch, and we will discuss about computer connections bit later. We do not have, well, I mean there are some kind of redundancy. We will discuss that. Okay. There basically you can think that the switch will enable communication from A to B, any A to any B. Okay. And there is these guys are cooled, as I said. So, this is water cooling. You can, there are pipes, you can see these pipes here, and water is flowing through that, and this water is basically going on top of CPU. Okay. There are conduits through water is flowing. So, air cooling, water cooling is much more efficient. Okay. So, this is one rack. Okay. So, you can have a look at this system sometime later. So, this is a motherboard for Param Sanganak. So, this is place for fitting the CPU, this is for RAM, okay, and network card is connected on this node, this is network card. Okay. So, anyway, this is very similar, but this is in fact pretty small card. Okay. So, we take a memory, whatever memory you have, like you cannot put in one motherboard more than, well, I think more than 8 TB cannot be put. 4 TB is IT, that no system has 4 TB memory. But if you look at the specs, ROM has facility for getting access to 8 TB memory. Okay. So, we need to put memory on the motherboard, and you can't put more than 4 TB. So, this machine, memory is huge. Shared memory architecture, well, we do not have very big memory, but our computer center has something like I think 768 GB in a shared memory machine. Okay, but now you can, I mean 4 TB is what you can put. More than 4 TB, it has to be hard disk. So, this is indeed connected to big memory, which is again one hard disk. One hard disk maximum is 20 TB. Okay. If you are very rich, then maybe you can get a special hardware with 40 TB. Okay, and we need petabytes of data, then we need to connect many hard disks together, and that also sits in the rack. So, hard disk is also sitting in the rack, which I did not mention it, but it is on the rack itself. So, rack has nodes, switch, cooling units and the hard disk. User does not need to know, but the system admin needs to know what is the partition. For user is full 1 petabyte is available, you can use wherever you like. They have partitioned it, I mean you can't, you will have your own quota, but you do not need to worry where your data will be. Your data may be in 2 different disks. Okay. Same file can be scattered across 2 disks. You heard of this called RAID system? I think it's maybe just for your information RAID, I do not know the full form. So, we have in our lab 8 hard disks, okay, I think 6 hard disks, okay, which has 36 terabytes of data. But what if one hard disk fails? Okay. So, the idea is the RAID system has redundancy. Okay. So, we have 4 of them. So, some data is not, your data is not sitting only on one disk, it is scattered. So, that even if one hard disk fails, it can reconstruct the file. Okay. So, backup RAID is more expensive because the data, well, you do not need double the space, but you need maybe 1.5 times the space of required capacity. Okay. There are, okay. So, RAID is for backup. So, many systems are connected by RAID, which will be more expensive and also with longer for saving the data